Assalamu alaikum. My name is Hassan, and it is my honor to open today's presentation on behalf of our team. With me are Muad and Muhammad, and we are presenting under the supervision of Professor Tariq. Our project is titled VRF Service Changing Performance Centralized versus Distributed Service Designs. We built and evaluated four multi-tenant network architecture inside a real EVNG virtual lab using Cisco routers, firewalls, and Linux server. The question we set out to answer is when every network engineer eventually faces, when tenants are isolated from each other by VRFs but still need access to share services. Which architecture gives you the best balance, performance, security, and operational simplicity? Problem VRFs isolate tenant, but every tenant still needs shared services, DNS authentication, logging, and internet access. How you deliver those services across VRF boundaries determines your performance, your availability, and your operational cost. We answer that with four designs. D0, distributed. Every tenant has its own private service copy, best isolation, highest resource cost. D1, centralized. One shared service instance connected through BGP route target leaking, most efficient, but one failure takes everyone down. D2A centralized with firewall. All the traffic passes through a Cisco firewall before reaching the shared surface. Full compliance inspection, but higher latency. D2B distributed with firewall per tenant service like D0 plus mandatory inspection like D2A, both isolation and compliance, highest complexity. We tested all four at a number of tenants 6, 10, 14, and 20 tenants, measuring performance, blast radius, and operational complexity. Our FNG lab has four segments, sharing a management network at 192.168.100.0/24 with Zabbix monitoring on management control, D0 router at 192.168.100.11, client switch carrying VLANs 101 to 106, service switch carrying VLANs 201 to 206. Each tenant has a Linux client and a Surface node, two subinterfaces per tenant on RD0. D1 router at 192.168.100.12 running BGP Autonomous 65000. One client switch, one share server at 10.255.0.10 inside VRF shared services, the simplest segment. D2A router at 192.168.100.13 with firewall between the router and the shared server. Per tenant transit links in the network 172/30 range. Firewall shared interfaces at 10.255.0.1. D2B router at 192.168.100.14 with firewall transit VLANs 301 to 306 in the network 172/30. 6 individual service node, 1 per tenant, 18 VLANs total. D0 is our baseline. Every tenant VRF it's self-contained, its own DNS authentication, logging, and the throughput sync. No inter-VRF dependency exists. So in DR0, each tenant gets two subinterfaces. For tenant 1, client gateway at 10.1.0.1/25 and service gateway at 10.1.0.129/25. Service node at 10.1.0.130 run DNS on port 53, HTTP authentication on port 80, syslog on port 514. All persistent systems services. Traffic path at 10.1.0.110 reach D0 tenant services in two hops. no leaking, no firewall, the shortest path in the project. Validation, all the service type confirmed working from D0 tenant Linux. If request tenant attempt return, destination unreachable, isolation hold completely. Now I hand it over to my colleague Muad.
You, Hassan. D1 solves the resource problem. Instead of n servers, we run one shared server and serves all tenants. The connection mechanism is BGP route target leaking. The shared prefix appears automatically in each tenant's routing table, no per tenant static route. As per security, we used ACL tenant to shared server is applied inbound on every tenant sub-interface. It allows only the dedicated service to 10.255.0.10. Everything else is denied. Cross tenants traffic is blocked completely. The path takes 3 or 4 hops longer than D0 because the packet move between VRF contacts inside the router. This adds latency but saves resources. D1 reduces servers count from n to 1, but blast radius harm all tenants. The critical weakness: if the shared server fails, every single tenant loses services. As for D2A, basically is the same as D1 but adds a mandatory firewall between tenants and the shared service. The goal is to prove that every packet was inspected. A static host route per tenant VRF forces all shared services traffic through the firewall. No alternative path exists. On firewall, each tenant has a named transit interface per tenants. ACL allows traffic only to host 10.255.0.10. ICMP inspection handles stateful returns traffic. We verified the firewall is a real hub using traceroute from all 6 tenants. 2 failure point, firewall down or shared service down, both take all tenants offline. As for D2B, combine both per tenant service instance like D0 and mandatory firewall inspection like D2A. Neither property is sacrificed. And here we have 18 VLANs for 6 tenants, 3 VLANs per tenants, one between the client and the router, one between the router and the firewall, and one between the firewall and the server. We validated this with 2 tests. Traceroute confirmed the firewall in all 6 paths, shutting down one server affected only tenant 1, while the other continuous. But service failure stays locally like D0. Firewall failure still takes everyone down like D2A. Muhammad will give you the analysis after me. After that, we have described all 4 uh, decision designs and stated the result. The simulation will now show those results happening: live packet animation failure, injection real-time metrics mechanism, our actual lab behavior exactly. And this is the metric that we tested. Now Muhammad will show you the performance metric.
Thank you, Mar. Let's view the performance metrics and measurement plan. Let's view the DNS latency for each design. For D0, we see that the latency from scaling up from 6 tenant to 20 tenant haven't changed much, because with the increase of tenants, we increase the number of servers that connected to that specific tenant. So there will not be any much load on one server. But if we inspect D1 and D2A, we see that there is a huge and noticeable increase in latency, because all the tenants added will have a huge load on the one server, the shared server. So we can see a huge spike in latency. For D2B, it will be similar to D0, but we'll have much more latency because the firewall will manage all the added tenants, unlike D0. For the blast radius, we can see that D0 and D2B, the VRF impacted will be the one that went down. So if we have 6 tenants and one of the servers are down, one VRF will be impacted. Same goes with the scale up. Even if we have 20 tenants, if one goes down, that specific VRF will be the only one impacted. Unlike D1 and D2A, where if the shared service is down, other VRFs will be impacted. So at 20 tenants, all of them will be impacted. Now, in conclusion, when do we choose D0? We want it when we have strict isolation required, low shared fate tolerance, and small to medium tenants. So what are the trade-off? It has the best blast radius, as we mentioned before, but has the highest footprint and operational cost, similar to D2B, where we have a huge cost. As for D1, when do we choose it? When we want to central manage our network, because we have one shared server, we can upgrade it and do all the configuration on that specific server. No need to move from one server to another. And when the resource is a concern of our network, it's one of the trade-off is the lowest cost for D1. D2A is similar to D1, but when we want to implement security measures, so we will add the firewall. So when to use, when compliance/security is of concern. Similar to D2B, we use it when the security is of concern, and we want a similar topology to D0. That's it for our presentation. Thank you for listening.